children, welcome to today's episode on atomic spectra, emission spectra and absorption spectra. Before going deep into the topic, let me share with you the learning objectives for today's lesson.
ਅੱਜ ਦੇ ਇਸ ਵਿਸ਼ੇ ਤੇ ਵਿਚਾਰ ਕਰਨ ਤੋਂ ਪਹਿਲਾਂ ਆਓ ਅੱਜ ਦੇ ਪਾਠ ਦੇ ਸਿੱਖਿਆ ਉਦੇਸ਼ ਸਾਂਝੇ ਕਰ ਲਈਏ। Define atomic spectra, emission spectrum, absorption spectrum, state
Bohr's model
of an atom. Describe spectroscopy, differentiate between emission and absorption spectrum. Explain emission spectrum of hydrogen atom and Rydberg Formula.
Children, I'm sure you all must have seen a rainbow in the sky. Have noticed that it consists of 7 colors? Violet, indigo, blue, green, yellow, orange and red, which can be remembered as Vibgyor. Have you ever thought why and how rainbow is formed? To understand this, let us first discuss what is a spectrum. Let us have a look at an animation to understand this better.
ਜਦੋਂ ਸੂਰਜ ਤੋਂ ਸਫੇਦ ਪ੍ਰਕਾਸ਼ ਪ੍ਰਿਜ਼ਮ ਵਿੱਚੋਂ ਲੰਘਦਾ ਹੈ ਤਾਂ ਇਹ 7 ਡਿਫਰੈਂਟ ਕਲਰਸ ਵਿੱਚ ਵੰਡਿਆ ਜਾਂਦਾ ਹੈ, ਜਿਸ ਨੂੰ ਸਤਰੰਗੀ ਪੀਂਗ ਕਿਹਾ ਜਾਂਦਾ ਹੈ, ਜਿਸ ਵਿੱਚ ਵਾਇਲਟ, ਇੰਡੀਗੋ, ਬਲੂ, ਗ੍ਰੀਨ, ਯੈਲੋ, ਔਰੇਂਜ ਅਤੇ ਰੈੱਡ ਕਲਰਸ ਹੁੰਦੇ ਹਨ। ਇਸ ਦਾ ਮਤਲਬ ਹੈ ਕਿ ਸੂਰਜ ਦੀ ਰੋਸ਼ਨੀ ਵੱਖ-ਵੱਖ ਵੇਵਲੈਂਥਸ ਦੀਆਂ ਇਲੈਕਟ੍ਰੋਮੈਗਨੈਟਿਕ ਵੇਵਸ ਦੀ ਬਣੀ ਹੋਈ ਹੈ। ਪ੍ਰਿਜ਼ਮ ਸਫੇਦ ਪ੍ਰਕਾਸ਼ ਦੀ ਵੱਖ-ਵੱਖ ਵੇਵਲੈਂਥਸ ਦੀ ਇਲੈਕਟ੍ਰੋਮੈਗਨੈਟਿਕ ਵੇਵਸ ਨੂੰ ਆਪਣੇ ਓਰੀਜਨਲ ਪਾਥ ਤੋਂ ਡਿਵੀਏਟ ਔਰ ਬੈਂਡ ਕਰ ਦਿੰਦਾ ਹੈ। ਲਾਲ ਰੰਗ, ਜੋ ਕਿ ਸਭ ਤੋਂ ਵੱਧ ਵੇਵਲੈਂਥ ਵਾਲਾ ਹੁੰਦਾ ਹੈ, ਸਭ ਤੋਂ ਘੱਟ ਡੈਵੀਏਟ ਜਾਂ ਬੈਂਡ ਹੁੰਦਾ ਹੈ, ਅਤੇ ਵਾਇਲਟ ਕਲਰ, ਜਿਸ ਦੀ ਵੇਵਲੈਂਥ ਸਭ ਤੋਂ ਘੱਟ ਹੁੰਦੀ ਹੈ, ਸਭ ਤੋਂ ਵੱਧ ਡਿਵੀਏਟ ਜਾਂ ਬੈਂਡ ਹੁੰਦਾ ਹੈ। ਇਸ ਤਰ੍ਹਾਂ ਪ੍ਰਿਜ਼ਮ ਦੁਆਰਾ ਸਫੇਦ ਪ੍ਰਕਾਸ਼ ਦੀ ਅਲੱਗ-ਅਲੱਗ ਵੇਵਲੈਂਥਸ ਦੀ ਇਲੈਕਟ੍ਰੋਮੈਗਨੈਟਿਕ ਵੇਵਸ ਨੂੰ ਵੱਖ ਕਰਨ ਨੂੰ dispersion ਕਿਹਾ ਜਾਂਦਾ ਹੈ। This pattern of 7 color of emitted radiation from prism obtained on the photographic plate is called spectrum. In this spectrum, there is continuity of colors, that is, one color merges into the other without any gap or discontinuity, and such a spectrum is known as a continuous spectrum. ਉਦਾਹਰਣ ਵਜੋਂ, violet merges into indigo, indigo merges into blue, blue merges into green, and so on. The continuous spectrum can also be obtained from the light emitted from some incandescent substances.
Let us now discuss what is a spectroscope. A spectroscope or spectrograph is an instrument used to separate radiations of different wavelengths and frequencies and analyze the spectrum. Let us now try to define spectroscopy. The branch of science dealing with the study of spectrum is called spectroscopy. It helps to study the electronic structure of atoms. Spectra is broadly classified into emission spectra and absorption spectra depending upon the source of radiation. Emission spectra are mainly of two types: continuous spectra and line spectra. Continuous spectra is obtained when white light is analyzed through spectrometer. A continuous band of 7 colors are obtained on the photographic film. The spectrum appears in a series of lines is called a line spectrum. The characteristic lines in atomic spectrum can be used in chemical analysis to identify elements. This line spectrum is also called the atomic spectrum because it originates as a result of absorption and subsequent emission of energy by the electrons in the individual atoms of element. Each element has a unique atomic spectrum and is different from other elements. The line spectra of an element indicates that an excited atom can radiate only a certain definite and fixed amount of energy. This leads to the conclusion that electrons present in an atom cannot have just any amount of energy, but only a certain fixed amount of energy. An atom consists of a small, heavy, positively charged nucleus in the center surrounded by electrons. The electrons in an atom revolve around the nucleus only in certain selected circular paths called orbits. These orbits are associated with definite energies and are called energy shells or energy levels. The energy of an electron in the orbit does not change with time. In other words, as long as the electron remains in a particular orbit, it does not lose or gain energy. This means that the energy of the electron in a particular energy shell remains constant. Therefore, these orbits are also called as stationary states.
Line spectrum observed in case of hydrogen atom can be quantitatively explained using Bohr's model. When an electron jumps from a lower orbit to a higher orbit, it absorbs energy. When the electron jumps from a higher orbit to a lower orbit, it emits energy. It is clear that each spectral line in emission spectrum can be associated to a particular transition in hydrogen atom. As large number of hydrogen atoms are present in a sample, different transitions can be observed giving large number of spectral lines. The intensity or brightness of spectral lines depends upon the number of photons of same wavelength or frequency absorbed or emitted. From the Bohr's atomic model, it is clear that electron can have only certain definite energy levels. When the electron is present as close to the nucleus as possible, the atom has minimum possible energy and is said to be in ground state. For example, in case of hydrogen atom, there is only one electron and this should be present in the lowest energy shell. When energy from some outside source is supplied to it, it can absorb a definite amount of energy and jumps to higher energy state. Such a state of an atom in which the atom possesses more energy than possessed in the ground state is called the excited state. This excited state is unstable and the electron tends to come back to lower energy level. This transition from upper energy level to lower energy level occurs with a jump and energy is emitted in the form of a quantum equal to difference in energies between the two energy levels. Each transition from one upper level to lower level will produce a light of definite wavelength. This is observed as a line in the spectrum of hydrogen atom. Thus, the different spectral lines in the spectra of hydrogen atoms correspond to different transitions of electrons from higher energy levels to lower energy levels. This is quite curious, and a question arises as to why spectrum of hydrogen has so many spectral lines although it contains only one electron. And the answer is, a sample of hydrogen gas contains a large number of molecules, and when energy is supplied by passing electric discharge, the hydrogen molecules split into hydrogen atoms. The electrons in different hydrogen atoms absorb different amount of energies. Therefore, these are raised to different energy states.
Let us now discuss more about the emission spectrum. The emission spectrum of an element or compound is the pattern of electromagnetic radiation of each frequency emitted by atoms of an element or compound when they are excited. Excitation is done either by passing electric discharge through a gas at low pressure or by heating the element or compound to high temperature. Atoms of the element that have absorbed radiations are said to be excited. For example, sodium or salt of sodium gives off yellow light, while potassium or salt of potassium produces a violet color. When the radiations emitted by different substances are analyzed through spectrometer, the spectrum obtained consists of sharp, well-defined lines separated by dark bands, each corresponding to a definite frequency or wavelength. Each atom's atomic emission spectrum is unique and can be used to determine if that element is part of an unknown compound. Similarly, the emission spectra of molecules can be used for chemical analysis. Let us discuss the emission spectrums of the sodium chloride salt. When sodium chloride salt is heated on the Bunsen flame, light produced is analyzed through spectrometer containing two yellow colored lines at a wavelength 5890 Armstrong and 5896 Armstrong respectively is obtained. These two colored lines are separated by dark bands. Dear children, let us now discuss about the origins of emission spectra and atomic excitation and de-excitation of electrons. Each atom of an element has got electrons. When the electrons in the atom are excited, for example, by heating, the additional energy pushes the electron to higher energy levels or orbits. When the electrons falls back down and leaves excited state, that is the de-excited energy, is re-emitted in the form of photon. Photon is a packet of energy which is present in light. The wavelength and frequency of the photon is determined by the difference in energy between the two states. These emitted photons form the element's emission spectrum. Each line in the spectrum corresponds to particular wavelength or frequency. The fact that only certain colored lines appear in an element's atomic emission spectrum means that only certain frequencies of light are emitted. Each of these frequencies are related to energy by the formula E is equal to h nu, where E is equal to energy of photon, nu is equal to frequency, h is equal to Planck's constant. Dear children, let us discuss about the absorption spectra. When white light is allowed to pass through a gas or a solution of some salt such as sodium chloride, and the transmitted light is analyzed through spectrograph, we obtain a spectrum on a photographic plate in which dark lines are observed in an otherwise continuous spectrum. These dark lines indicate that radiations of the corresponding wavelengths have been absorbed by the substance from the white light. Such a spectrum containing a few dark lines due to absorption of some wavelengths of white light by gas or solution of some salt is known as absorption spectrum. The dark lines of definite wavelengths are also characteristic of the substance. When sunlight is passed through sodium chloride solution and then analyzed through spectrometer, two dark lines appear exactly at the same place where two colored lines are obtained in the emission spectrum of sodium vapors. Thus, two dark lines at wavelengths 5890 Armstrong and 5896 Armstrong respectively is obtained in the continuous spectrum. Dear children, now we will try to understand continuous, emission and absorption spectrum with the help of animations. When white light from sun is passed through a prism, it splits into a series of continuous color bands known as rainbow of colors. A similar spectrum is produced when a rainbow forms in the sky. This means that sunlight is composed of collection of electromagnetic waves having different wavelengths. The prism bends the light of different wavelengths to different extents. The red color with the longest wavelength is deviated the least, while the violet color with the shortest wavelength is deviated the most. In this spectrum, there is continuity or overlapping of colors, that is, one color merges into others without any gap or discontinuity. Such a spectrum is known as continuous spectrum. For example, violet merges into indigo, indigo merges into blue, blue merges into green, and so on. The continuous spectrum can also be obtained from the light emitted from some incandescent substances. When electric discharge is passed through hydrogen gas and the radiation emitted through hydrogen gas is analyzed in a spectroscope, we obtain spectrum consists of bright large number of sharp colored lines separated by dark spaces. Such spectrum is known as emission spectrum. When sodium salt is heated on the Bunsen flame and light emitted is analyzed through spectroscope, yellow colored lines separated by the dark bands is obtained on the photographic plate is shown in the animation. When white light is passed through a solution or vapors of chemical substance such as sodium chloride and the transmitted light is analyzed in a spectroscope, the spectrum consists of two dark lines in yellow region of continuous spectrum. Such spectrum is called absorption spectrum. Students, look at the absorption spectrum of hydrogen atom as shown in animation. The origins of these three types of spectrum are illustrated in the figure which you are seeing on the screen. Students, look at the emission and absorption spectrum of hydrogen and then emission and absorption spectrum of sodium. use of spectroscopy. Identifying the composition of stars by analyzing the received light. The emission spectrum is used to identify elements present in a substance. Spectroscopy is used for X-ray in hospitals. Dear children, let us discuss about the Bohr's model. Bohr's model for hydrogen atom shows two-dimensional model of atom. The Bohr's model is probably familiar as the planetary model of the atom, which is used as a symbol for atomic energy. In the Bohr's model, the neutrons and protons occupy a dense central region called the nucleus, and the electrons orbit the nucleus. Only in certain selected circular orbits, much like planets orbiting the sun, these orbits are associated with definite energies and are called energy shells. The energies of stationary state in case of hydrogen atom are given by the expression shown on the screen. Energy of electron in nth shell is equal to minus RH multiplied by 1 divided by n square, where n is equal to 1, 2 or 3, where RH is called Rydberg constant. Angular momentum of electrons in atoms is quantized. As long as the electron remains in a particular orbit, it does not lose or gain energy. This means energy of an electron in a particular orbit remains constant. These orbits are called stationary states. When energy from some external source is supplied to the electron, it may jump to some higher energy level by absorbing definite amount of energy. When the electron jumps back to the lower energy level, it radiates same amount of energy in the form of a photon of radiation. Dear children, let us discuss about emission spectrum of hydrogen atom. The spectrum of hydrogen is very important in astronomy because most of the universe is made of hydrogen. The spectrum of hydrogen atom can be obtained by passing an electric discharge through the gas taken in the discharge tube under low pressure. The emitted light is analyzed with the help of spectroscope. Emission process in hydrogen give rise to series, which are sequences of lines corresponding to electronic transitions. The spectrum consists of large number of lines appearing in different regions of wavelengths. Some of the lines are present in the visible region, while others in ultraviolet and infrared regions. In 1885, J.J. Bohr developed a simple relationship among the different wavelengths of the series of visible lines in the hydrogen spectrum. The Bohr formula explains only the spectral lines in the visible region. These series of lines which appear in visible region were named Bohr series. Soon afterwards, a series of spectral lines of hydrogen atoms in different regions were discovered. These lines in different regions were grouped into 5 different series of lines, each being named after name of its discoverer. These are Lehman series, Bohr series, Paschen series, Brackett series and Infant series. Lehman series appears in the ultraviolet region, Bohr series appears in visible region, while the other 3 series lie in the infrared region. Rydberg Formula. Although a large number of lines are present in the hydrogen spectrum, Rydberg in 1890 gave a very simple theoretical equation for the calculation of wavelength and frequencies of these lines. The equation gives the calculation of wave numbers of the lines by the formula
1 upon lambda equals to r multiplied by 1 upon n1 square minus 1 upon n2 square, where r is a constant called Rydberg constant and has a value equal to 1.097 multiplied by 10 raised to power 7 meter inverse. N1 and N2 are the whole numbers, and for a particular series N1 is constant and N2 varies. Also, N2 is greater than N1. For example, for Lyman series, N1 equals to 1, N2 equals to 2, 3, 4. Ultraviolet region. For Balmer series, N1 equals to 2, N2 equals to 3, 4, 5. Visible region. For Paschen series, N1 equals to 3, N2 equals to 4, 5, 6. Infrared region. For bracket series, N1 equals to 4, N2 equals to 5, 6, 7. Infrared region. For fund series, N1 equals to 5, N2 equals to 6, 7, 8. Infrared region.
We also know that C is equal to nu multiplied by lambda as shown on the screen, where C is the speed of light, which is equal to 3 multiplied by 10 raised to the power 8 meters per second, and nu is frequency. Children, we have studied today what is spectrum and spectroscopy. We also studied about emission spectra and absorption spectra. We also discussed the origin of these three types of spectra. We also studied about emission of hydrogen atom. Lastly, we discussed about Rydberg formula.
Knowledge check. So now we come to the end of today's topic. Here's a quick test for you to find out how much you have actually absorbed by solving a problem. Question is, what is the wavelength of light emitted when the electron in the hydrogen atom undergoes transition from an energy level with N2 is equal to 4 to an energy level with N1 is equal to 2? What is the color of emitted radiation? Let us now have a look at the solution. According to Rydberg equation, 1 upon lambda is equal to r multiplied by 1 upon n1 square minus 1 upon n2 square. Here, n1 is equal to 2, n2 is equal to 4 and r is equal to 1,09,677 centimeter inverse, or 1 upon lambda is equal to 1,09,677 multiplied by 1 upon 2 square minus 1 upon 4 square centimeter inverse, which is equal to 1,09,677 multiplied by 12 divided by 64 centimeter inverse. We can also say that lambda is equal to 64 divided by 1,09,677 multiplied by 12 centimeter, or lambda is equal to 486 multiplied by 10 raised to the power minus 9 centimeter, which is equal to 486 nanometer. This line corresponds to bluish green color. My next question is, in the Rydberg equation, a spectral line corresponds to N1 is equal to 3 and N2 is equal to 5. Calculate the wavelength and the frequency of this spectral line. To which spectral series does this line belong? In what region of the electromagnetic spectrum will the line fall? Let us now have a look at the solution. According to the Rydberg equation, 1 by lambda is equal to R into 1 by N1 square minus 1 by N2 square, where R is equal to 1,09,677 centimeter inverse, N1 is equal to 3, N2 is equal to 5. Substituting these values, 1 by lambda is equal to 109,677 into 1 by 3 square minus 1 by 5 square centimeter inverse, or is equal to 109,677 into 1 by 9 minus 1 by 25 centimeter inverse, or we can say 1 upon lambda is equal to 109,677 into 16 by 225 centimeter inverse. Therefore, lambda is equal to 225 by 109,677 into 16 centimeter, which is equal to 12.82 multiplied by 10 raised to the power minus 5 centimeter, which is equal to 1282 into 10 raised to the power minus 9 meters. Or we can say lambda is equal to 1282 nanometers. Now, lambda multiplied by nu is equals to c, or nu is equal to c by lambda, where c is equal to 3.0 multiplied by 10 raised to the power 8 meters per second. Or we can say lambda is equals to 1282 multiplied by 10 raised to the power minus 9 meters. Therefore, nu is equal to 3.0 multiplied by 10 raised to the power 8 meters per second divided by 1282 multiplied by 10 raised to the power minus 9 meters, which is equal to 3 by 1282 multiplied by 10 raised to the power 17 seconds inverse. That is equal to 2.34 multiplied by 10 raised to the power 14 seconds inverse. Now let us come to the solution of the second problem. Since this line corresponds to N1 is equal to 3, it belongs to Paschen series. Now we come to the solution to the third problem. The spectral line will fall in infrared region.
ਬੱਚਿਓ, ਮੈਨੂੰ ਉਮੀਦ ਹੈ ਕਿ ਤੁਹਾਨੂੰ ਅੱਜ ਦਾ ਇਹ ਪਾਠ ਕਾਫੀ ਦਿਲਚਸਪ ਲੱਗਿਆ ਹੋਵੇਗਾ। ਧਿਆਨ ਦੇਣ ਲਈ ਸ਼ੁਕਰੀਆ। ਅਗਲੀ ਵਾਰ ਇੱਕ ਹੋਰ ਨਵੇਂ ਵਿਸ਼ੇ ਨਾਲ ਫਿਰ ਮਿਲਾਂਗੇ। ਤਦ ਤੱਕ ਲਈ ਇਜਾਜ਼ਤ ਦਿਓ।